So far in this chapter, we've been talking about different kinds of reactions in aqueous solutions. Well, not exactly different. We've only discussed one, and that's precipitate reactions. That's going to be a huge part of your upcoming lab. Today we're going to start talking about acid-base reactions, and those also happen in water. Then we're going to talk about redox reactions. These are two vocab words you totally need to know, and that's concentrated versus dilute, which of course doesn't have anything to do with strong or weak. Those are two very different words. Concentrated versus dilute, this describes the number of particles, and we measure the number of particles by the number of moles in a solution. That's my abbreviation for solution, remember? And we actually have a value called molarity that we use to measure that. And molarity's symbol is a big M, and we measure it in moles per liter. Out of these two pictures, which one would you say is more dilute? Well, we can actually use numbers to describe it. If I picture each one of these little balls in here as being a mole, so we'll pretend that this is 1 mole, for every, and the box is 1 liter. There we go. Then this would have a molarity of 1. Now this box, on the other hand, has 28 little balls, I think, I counted them, for every 1 liter. Well, that would give it a molarity of 28, which is pretty much impossible, but just run with it. Well, which one of these two solutions is concentrated? The one with the bigger number, because the numerator's large, this number's large. So we actually have a number to help us measure concentration. We call it molarity. Now, if you recall from our discussion on electrolytes, strong versus weak, these are chemistry terms. They have absolutely nothing. They do not equal concentration. Concentration, again, from the previous slide, is the number of particles in the solution. It has nothing to do with strong versus weak. That's the chemistry. If something is strong, it means it's 100% dissolved, or darn close to it, in the solution. So if I took hydrochloric acid, an aqueous solution, put it in water, it's going to 100% break apart into hydrogen ions and chlorine ions. The word weak, again, has nothing to do with concentration. Weak means it is less than 100% dissolved. So if I take hydrofluoric acid, dissolve it in water, make an aqueous solution in water, some of it breaks apart into the two ions, but notice this, some of it stays as HF, and you can see that here in this picture. That's what a weak solution is. Is it possible to have a weak acid be very concentrated and thus very dangerous? Is it possible to have a strong acid that is very dilute and therefore not dangerous? That's worth extra points to put that down in a sentence. Or answer those questions, rather. Now this picture obviously is not on your packet, but it just is an example to show you that if it's a strong acid, by definition, it dissolves 100% into its separate ions. There are only 7 strong acids that you need to know, and of course, by that I mean memorize. The first 3 are pretty easy to remember. We have hydrochloric acid, hydrobromic acid, and hydroiodic acid. If you look on the periodic table, chlorine, bromine, and iodine are all halogens. So hydrochloric, hydrobromic, and hydroiodic acids. Then we have nitric acid, sulfuric acid, chloric acid, and perchloric acid. All 7 of these will dissociate 100%. Now, acids have specific properties. The first one is they do conduct electricity. Why? That's worth extra points. Tell me why an acid would conduct electricity. Acids do taste sour, that's true. And they do react with some metals to produce hydrogen gas. Okay, the big important one that you absolutely need to know is this chemical formula. If you take an acid, mix it with a base, the word alkali means base, you get salt and water. That's hugely important to know in this chapter. If we use an indicator, which changes color in the presence of an acid or a base, and you'll be using in your lab universal indicator, and it's really cool stuff because it does change color. It changes color that in an acid becomes red. Bases will turn blue when you put an indicator in it, and neutral colors, the indicator turns green. You should probably write that down and know that. Now, this probably is the most important part of the chemistry of an acid. To be considered an acid, you have to have an excess number of hydrogen ions in the solution. So acids produce hydrogen ions. Remember, let's try a new one. Let's take nitric acid. It's going to dissociate into hydrogen ions and nitrate ions. This is why it's an acid. The most interesting thing I think about the hydrogen ion is really the hydrogen ion is simply a proton. Why? Why is the hydrogen ion simply a proton? Answer that question, it's worth extra points. The pH scale is what we use to measure whether something's acidic or basic, or alkaline, which means basic. All right, the pH scale technically means potential of hydrogen, which I think is really hard for most students to understand. I like to think of it as parts of hydrogen. Now, because it's a logarithmic scale, it seems kind of backwards because the more hydrogen ions you have, the lower the number. And the fewer hydrogen ions, the higher the number. But if you think about water, and water dissociates, remember, water dissociates into hydrogen ions and hydroxide ions, HOH. This side of the scale, from 7 over, you have hydrogen ions. From 7 above, you have excess hydroxide ions, therefore it's a base. This direction, you have excess hydrogen ions, so it's an acid. If it's 7, the hydrogen ion concentration equals the hydroxide ion concentration, which only happens in pure water at a certain temperature, and that's a neutral, 7. Okay, of the 7 strong acids that we have, hydrochloric acid would dissociate in water how? How about hydrobromic acid? How would that dissociate? Like that. And hydroiodic acid, how would that dissociate? Oh, there's the hydrochloric acid. Sorry, that was out of order. Like that. On the previous slide, I asked you to dissociate, or I showed you rather, the dissociation of 3 of the strong acids. On this slide, how would you dissociate nitric acid? Give it a try. How would you dissociate sulfuric acid? There's something wrong with this. Do you know what it is? I do. I should have had a 2 right here. Now try dissociating chloric acid. Lastly, dissociate perchloric acid. Well done. Strong bases, on the other hand, produce hydroxide ions in solution. You need to be OH to be a strong base, and it has to be an ionic compound. For instance, if I had something like this, CH3OH, this guy is not a base. That is not an ionic compound. So you have to have a cation plus OH to be a strong base. And if you recall, hydroxides are insoluble in water, so it needs to be paired up with a group 1 metal. Now the group 1 metal, do you remember the name? Yeah, those are alkali metals, because when you put an alkali, which means base, if you put an alkali metal in water, you make a base. Some properties of bases, well, they do taste bitter, like Brussels sprouts or the stem of a cucumber or soap. If you've ever had your mouth washed out with soap before, you know how bitter that is. Bases also feel soapy or slippery. Most of your household cleaning products are bases. And they produce hydroxide ions in solution. That's the key right there. Hydroxide ions in solution. So the products, if I give you a reaction that contains a strong acid and a strong base, you will always end up with the same two products, salt and water. So let's take a look at this. We have sodium hydroxide. We know it's a base. It ends in hydroxide and it's an ionic compound. Sulfuric acid's one of the 7. Notice it double displaced. Sodium with a +1 charge, hooked up then with sulfate, which gave us NO2SO4. Then hydrogen, which has a +1 charge, and hydroxide with a -1, well, that became water, which is HOH. And then the equation then is balanced. That is your molecular equation. How would you write a complete ionic equation for this? Go ahead and pause the video and give it a try. Well, we have 2 sodium ions plus 2 hydroxide ions plus 2 hydrogen ions plus 1 sulfate ion. And sodium sulfate is soluble because it starts with soluble. Well, because it starts with column 1, and those are soluble. So we have 2 sodium ions and 1 sulfate ion. But water is a liquid. This is our product, folks. This is what we made. This is what did the chemistry. So we're going to leave that one alone as H2O, liquid. And yes, you could write AQ next to all of those if you'd like. If you don't, it's fine, but you make sure you write the liquid next to the water. The key question now is, well, there's your molecular, there was your complete ionic. What's the net going to be? Well, we know this is our product. So what 2 things went into making the water? The hydrogen ions and the hydroxide ions. So go ahead and pause the video and see if you can come up with the net ionic equation. I end up with 2 hydrogens plus 2 hydroxides. Remember to write the positive first. Gives us 2 waters. Make sure you write the liquid. Do you see a problem here? There is a small problem. It's reducible. So we're going to take these 2's right out of there. Ladies and gentlemen, for a reaction with a strong acid and a strong base, I have good news for you. This is always going to be the net ionic equation for a strong acid and a strong base, always. So let's try this one. We want all 3 equations. Go ahead and pause the video and see if you can come up with all 3. So we need a molecular equation. So nitric acid's one of the 7. It's HNO3. It is aqueous, plus potassium hydroxide, which is also aqueous. So that ends up being potassium nitrate, and potassium and nitrates are always soluble, so there you go, plus water. And that's our product, that's liquid. It is balanced, I have all of my subscripts, we're good to go. Now we need the complete ionic equation, complete ionic. So that means break everything apart as it exists in the solution. So we end up with hydrogen ions plus nitrate ions plus potassium ions plus hydroxide ions yields potassium ions plus nitrate ions plus water. That's the product. That's what did the chemistry. So, did you get a net yet? So our net ionic equation, remember, we made water, so what two things went into that? The hydrogen ions and the hydroxide ions. Hydrogen plus OH yields water. Make sure you write the liquid. Oh look, just like I promised you, the same net ionic we saw in the previous slide. Number 7 is one I want you to do on your own and show me this problem when you have it completed. Ideally, that would be tomorrow. These are up to you if you want the extra points or not, but to go ahead and give them a try. Up next, I guess there was only one extra credit, sorry. Up next we have redox reactions.